kind of place where stars move through, because everything is rotating around the North Star, coming up in the east, going down in the west, counterclockwise as we look up. And we're looking down, the Earth is going counterclockwise as we look down. So you could say the celestial meridian is typically talked about in the same breath as the celestial sphere, because we use it to see how the celestial sphere moves.
Is it kind of like the prime meridian for Earth?
Okay, so the prime meridian for Earth would be essentially a 0 point on the celestial sphere. Now I don't know, I think it might be, I'm not sure if it is 0 hours of right ascension, I have to look that up. But it would correspond to a particular place of going around in 360 degrees or 24 hours in that clock. Now, that would be, that particular thing, any point of right ascension is like a meridian on the Earth. It's, basically fixed to the, it's fixed on the celestial sphere itself. Now the prime meridian, let's see, the prime meridian is fixed to the Earth, so the celestial meridian is like the prime meridian, no, it's fixed to the Earth. But it's fixed wherever you are. One more. Path of the sun through the sky. What is that?
The ecliptic.
The ecliptic.
Ecliptic.
So we say the path of the sun through the sky, but it's really the apparent path of the sun through the sky. And it's the apparent, it's every day. And it's the apparent path of the sun, let's see, is that right? Well, it's the apparent path certainly during the year as the sun moves through the celestial sphere. But basically the sun moves along that kind of path because it represents the plane of the Earth's orbit. So the Earth orbits and orbits around the sun, and that forms a plane, and you slice that through the celestial sphere, and that's the ecliptic. Okay, let's see, the ecliptic, the equator of the Earth is tilted. I don't know if we talked about it. Yeah, we mentioned it, I guess. Say here's the equator of the Earth. So the celestial equator would be out here. And then here is the ecliptic. Here's the sun here. So the ecliptic would sort of slice through this equator at certain points, basically. And then this angle is how much, do you know?
20, yeah.
24.5.
Yeah, about 23.5 degrees.
Yeah, that's what.
That's the tilt. And so basically, when you look at the ecliptic, let's see if we can.
I always remember the third number in a second.
Maybe I can draw it.
I knew it wasn't almost, it was like close to 24, but not quite.
If I do this celestial sphere, and this is the equator, then the ecliptic looks something like this on the celestial sphere. And this is 23.5 degrees that tilt, due to the tilt relative to its orbital plane. So the axis of the Earth is tilted 23.5 degrees relative to the orbital. All right. How many constellations are there in the celestial sphere? 88. 88, exactly. Okay, so you see about half of them at a time, maybe a little bit more at night because of the way things rotate around. On the equator, you can see almost all of them, if not all of them, in a single night. Because the equator, you see the half of the sky, and then that whole thing rotates. If it's through 12 hours, then you get to see the other half during the night. No place else you don't see part of the celestial sphere.
At the very least, through the course of the year, you would. I mean, that'd be
Yeah.
obscured by
Through the course of the year.
Yeah.
Through the course of the year, what?
You'd see the,
see all of them.
all the stars.
Not from the northern hemisphere, no.
No,
That-
No,
I was
meant
talking about from the
anywhere else.
equator through the course of the year as the.
Oh, yeah, at any
Yeah.
particular time, that's right.
Yeah.
That's right, at any particular time of night through the course of the year, then you'll see all of them, that's true. Another way. Okay. What are the equinoxes?
2 days of the year that time is equal.
Yeah, basically it's where the, let's see, how should I say, the intersection, I'll say it another way, but your way is correct. An intersection of the ecliptic with the equator. I call it the celestial equator. And we have the spring equinox, that basically the sun passes a point. That means it divides the day into 2 equal parts, night and day are equal. And vernal equinox around March 21st or so, and then autumnal around September 21st or so. Okay, it splits the day into two. How about the solstices? What are they?
Longest and shortest day of the year.
Longest and shortest, yep, that's right, longest, shortest day of the year, or the time
difference.
at which the, summer, they're basically the time of maximum distance of the sun from the equator on the celestial sphere. So the peak, the solstice, okay, let's even put a point out here. Say, typically we say this, the sun has a path going upward at the vernal equinox, that's, the vernal. And that has a measure of ascension. Ascension is, instead of talking about longitude on Earth, we talk about ascension, or right ascension on the celestial sphere. And that vernal equinox is 0 hours. 0 hours, 0 minutes. And then the vernal equinox in the sun goes up to the summer solstice. That's about June 21st. And then goes down here through the autumnal equinox. And then back down to the lowest point, and then say this north celestial pole here, south. I guess I would have to go here. Well, then it's the winter solstice.
What day is that?
That would be December 21.
Oh.
Now, we say that always from the northern hemisphere's point of view. From the southern hemisphere's point of view, that's the peak of summer down here. And this would be the peak of winter over there on the southern hemisphere. All right. Okay, solstices. What causes the seasons on Earth? Now, we didn't really talk about that prior to know the answer.
Our orbit and tilt around the sun.
Yeah, that's very good. Orbit and tilt, both. That's correct. Very good. Plus tilt. Okay. If you didn't have an orbit, if you didn't have an orbit, it would just crash into the gravity. But basically, as it goes around, as it orbits, then the tilt causes the northern hemisphere to be tilted either toward the sun near the summer solstice or away from the sun in the winter solstice as it goes around. So tilt is like a gyroscope, so tilt remains the same throughout the orbit. Okay. So tilt's like this all the way around.
With precession, of course.
Well, yeah, okay, that's another story. So basically, if you see the tilt's gonna be the same, and then you're gonna be tilted toward or tilted away. Now, what does that do? The sun's rays will strike the earth either more or less toward the perpendicular than this during the summer or winter respectively. This is what it is. So here, where the sun's rays are coming straight down, here actually at 23.5 degrees at the summer solstice. Once it gets over here, same angle, but now they're tilted away from, you know, say we're here, they're they're very close to vertical over here, in June 21. But on December 21, then they're tilted way away. You know, here's this angle, a big angle. So the sun is really much farther down on the horizon. How many people have been up north to Montana or Washington or something?
Canada?
Okay, Canada. So during the winter, you know, the days get pretty short. And the sun, it hardly gets up. It's like the sun is still asleep, half asleep, it's going across the sky.
My friend went to London and he said that the sun came up at like 4 o'clock and didn't go back down until like 11 p.m.
In the summer,
Okay, that's
right? So when you get way up north, and then it stays up longer, or in the summer, it stays up shorter in the winter. Because basically the higher you go, say you're up here, then you're looking down here, and as you go around and the sun sets, it comes back up really early when you have radiation way up there. Maybe that's hard to see. You probably need a real thing with a light shining. Basically, at the Arctic Circle, you can think of it this way. Say at the equinox. Then the sun is shining, and as the Earth goes around, what's going to happen to the sun? Right in the middle of the year. Say if you're at the North Pole.
What's gonna happen with the sun?
Well, you'll
You'll
probably
still
see it.
yeah.
If you get to the winter months, it'll go into darkness. But if you get in the equinox, basically you're halfway through. You know, this rope may be tilted this way. Then you're gonna go. It's gonna spin. Basically, the sun's gonna go like that. It's gonna be near the horizon the whole time.
Yeah.
And so, now in the winter, then it's going to be tilted away all the time, so you're not going to be able to see the sun at all. 24 hours of darkness for a period of time, closer you are to the North Pole. Yeah, I think there's a lot of, what do you call it, mood affective disorders, long nights, and the night would be, I don't know how many months long.
So at least like 6 weeks of unbroken darkness or something.
Maybe something.
It's a good thing penguins can't get depressed. At least as far as we can tell.
Oh, we didn't finish, okay, orbit and tilt. Okay, so, if you have, let me just expand on that. If they're direct rays of the sun, then, say the sun, this rays is coming like down a tube, then it's all that intensity in that tube is focused on like a circle, because direct rays. But on the other side of the Earth, that same tube comes at a slant, so that you have the same amount of energy over a larger area. That means the intensity, which is the rate of energy per meter, is higher when it's direct and lower when it's indirect, or you have a slant. And it's the intensity that determines how hot we'll get on the surface, how much absorption there is. So during the summer, we get a lot of energy. It's this rain, basically the sun. We can think of it like rays coming out. but they're actually particles, so it's like a rain. You know, I've seen people with umbrellas, you know, to protect yourself, especially, I don't know, in Asia, so you protect your skin, a lot of it, especially the women, but my wife does that.
18th
It's like
century
a
England with
rain
parasols.
The parasols, yeah.
All right, where is it? How long is the solar day in hours and minutes? Yes.
24 hours exactly.
Exactly. So the solar day is 24 hours exactly, 0 minutes. How about the sidereal day?
23 hours and 56 minutes.
Good, good, okay, 23 hours, 56 minutes. So it goes around once relative to the fixed stars, quote unquote, the stars on the celestial sphere. And then you've moved in the orbit a little bit, so now you're sort of peaking beyond the sun, where it was before, you're going looking straight through the sun. Now you peak beyond it, so to get to the solar day, you have to rotate a little bit more. You have to rotate 4 minutes more to get to the solar day, where it's straight, you know, at its highest point, maybe midday to midday. Okay. How about the planets? Does anybody know the planets that were conjunct in the last week or two? If you look out tonight, you should see in the southwest, so that's south, so you should see up here, Saturn and Mars. You know, they're in the same part of the sky. I think, you know, Mars is probably gone ahead, so Saturn looks like, this means, you know, the line isn't straight up and down, but maybe it's sort of tilted to the side. So we have Saturn and Mars. And that was August 24th. And then I think it was the 21st. Now this is something you got to be careful about, but right after sunset, then if you have a good vantage point to look, not at the sun, but after the sun sets, immediately after the sun sets, like 10 minutes or so, then you could see actually 3 planets, Venus, Jupiter, and Mercury. And on the 21st, it was Venus and Jupiter. Those are the 2 brightest planets in the sky. And they were on top of each other. I wonder if we have, let me see if I can bring up a picture. See if I can find it. Oh, it was 27, so just a few days. So here's what it would look like maybe just a few days ago. Venus and Jupiter and Mercury from someplace, so it was 40 minutes after sunset. Right, this would be in northern hemisphere probably. Now, I think some of these sites have a southern hemisphere in view. Let's see if they do. Nah. Oh, here's a picture. From Bangladesh. I don't know if you can see it or not. Let's see. Nah, it doesn't look good. I don't know if you can see Mercury. You can't see, it's probably behind the haze, but Venus and Jupiter, there's a lot of haze or clouds, but you can see how close they are. I think that occurs once in a long time, like 50 years, or I forget what these are. It might say in here, so. Oh, here's a picture, or kind of a simulated picture, artist depiction of the conjunction in the southern hemisphere. Now look at the difference in where you see Mercury relative to these. It's very interesting. It's hard to see. Okay, let's do it this way. So up here you see Mercury is well below these two. Not far below.
Close.
Really? Okay. And from the southern hemisphere, Mercury's above them. How come?
Point of view.
Point of view and perspective. So that, even that little distance between the northern and southern hemisphere produces a significant apparent movement of Mercury against the background sky. We call that effect, anybody know what that effect is? What is it called?
Parallax?
Parallax, yeah.
Oh, parallax.
I like had it right after
Basically,
you
say
did
if
that.
here's the sun, then Mercury is right here. In the northern hemisphere, it looks like it's down here. But from the southern hemisphere, it might look like it's up here. Now, that's exaggerated, obviously, but I don't know how many degrees that would be, but it might be a degree, which is a huge amount of distance in the night sky. And we'll talk about parallax too. Okay, so a lot of cool stuff. All right, we talked about the sidereal day and the solar day. Now, you're going to see this, so you have to know something about it. This will come up. Now, I will say, I guess I can just do it. How should I say this? I wonder, well, I'll try to break up something. Say you have the, what's his name? Who's the Warriors guy that's really good?
Stephen Curry?
Huh?
The
Steph-
lefty that's-
That was Steph Curry during the finals. Sorry. During the last couple of games, I think he got worn out. They tried to guy, and he was also injured.
Harrison Barnes.
Okay, so let's see, if you
Savage.
look at Polaris, then basically you have circles of declination. So Polaris is has a declination of about 89. So about let's see, we have right ascension and declination. Declination goes from 0 to 90 degrees, to plus 90 or minus. So 0 is at the equator, and plus 90 is the north celestial pole. Minus 90 degrees is the south celestial pole. Polaris, let's say the north celestial pole. If we look at, I think we talked about this the other day maybe, but basically, as we said, at the equator, if you're at the equator at night sky, there's south pole, there's north pole, you walk north and it tilts everything. So the equator is out there and it tilts it. So if you get up to here about 38 degrees, the north celestial pole in Polaris about is tilted up how far north you went. And that's whatever latitude you're at. the north celestial pole is at, and there's also, so we have right ascension declination, but it has an altitude of the latitude. So there are two ways to look at the night sky. Basically, it's a very natural thing to say, oh, there's north, there's south, there's east, there's west. That's 0 to 90 to 180 to 270 to 360 or 0. That's called azimuth. So altitude, and azimuth is north 0 degrees, east 90 degrees, south 180 degrees, west 270 degrees. So you can see, oh, well, there's east, there's south. Well, there's a star, and it has this sort of orientation around this 360 degrees, but it also has altitude. And you can measure the angle between the horizontal and down. That's the altitude. So, and you say 0 to 90. 90 degrees is zenith. What's zenith? What is zenith? Straight up. Okay, straight up. Okay, so if you say, now the equator is basically intersects the horizon due east. So the equator, the celestial equator, basically goes from the east and then into the west. And the celestial meridian goes again from north, 0, through zenith to south. So north, maybe I should say, celestial meridian. They go through zenith, the zenith, whereas the equator basically goes up to its maximum height. Around here, it's 90 minus the latitude. Latitude, you north, you tilt everything up. Latitude, so it's 90 minus the latitude. Latitude here is 38 degrees. That would be 90 minus 38 is 52. Max, basically max height of the celestial equator is 52 degrees. That's where it intersects the celestial meridian, CM, celestial. So celestial meridian, it goes right through there. It's a maximum height, 52 degrees. We call that basically the transit, where it goes through. Okay, so these are kind of astronomy terms when you're looking at the sky, trying to figure out where things are. Stars, and here, right ascension goes from 0 hours to 24 hours, everything in between. Starts at the vernal equinox, goes all the way around. Basically the summer solstice, that's 6 hours. The autumnal equinox, so it's a 0 hours vernal equinox. 6 hours is summer solstice. 12 hours is where the autumnal equinox is. And 18 hours is winter solstice. In terms of what we call the position of the sun at those particular, that's where the sun is on the vernal equinox at 0 hours, it's at 6 hours. At the summer solstice, 12 hours as the autumnal equinox, 18 hours at the winter solstice. So right ascension declination is a way to describe the positions of the stars. The stars rise in the east, set in the west, so the altitude and azimuth are always changing, always changing. But the right ascension declination, they're fixed points on the celestial sphere. They don't change. So if you look up in a table, you have a table of stars, and it gives us particular value of the right ascension, particular value of the declination. It's because it's like latitude and longitude in the Earth. That doesn't change unless the Earth moves or something. Now stars do move, but they're very, very slow. in their motion, so it'll take, decades before you have to adjust the tables, based on the precision that you usually see. Okay, now, this over here, we're talking about hours and degrees. You can separate a degree, say a circle is 360 degrees. And then so you can look at 1 degree. Now, if you look up in the heavens, then maybe 1 degree of arc. 1 degree of arc is about the size of your small fingers at arm's length. So small finger width at arm's length. And if you hold a fist, that's about 10 degrees. Because you can go like this, right? So you go, here's 10, that's the horizon, 20, 30, 40, 50, 60, 70, 80, 90 is right overhead. That's 10 degrees is a fist width. Maybe these 3 fingers is about 5 degrees. If you go like, let's see, what is it? Let's see. Like this is about 15 degrees, and like this is about 25. So 15 is like this, and 25 is like that. So you can get an idea of the distance between things in terms of their angle on the celestial sphere from one place to another. So we don't really measure distance in real distance ordinarily when we look at the sky, because we don't know how far it is unless you really get into the depths. Oh yeah, we found out how from parallax it's this far. Then we can really determine length in kilometers. Really, we talk, oh, how far is that? Well, it's about 10 degrees. Oh, that's gee whiz, it's way over, that's 25, maybe that's 35 degrees between those two. Now, a circle can be divided into 360 degrees, and then 1 degree can be divided into 60 minutes. Minutes are at this little dash, not dash, but single apostrophe, or we say 60 minutes. And then 1 minute can be divided into 60 seconds. And this is seconds of arc, not time. So it's just 1/60th of a degree